This is the improved high step-up DC to DC converter with a built-in transformer, and also active clamp is included here. This is the simulation circuit. Here we are using 16 volt supply, DC supply, and we are stepping up to 400 volt. This can be done, this is done by using a built-in transformer with step up ratio of 5. That means 5 times it will step up the voltage. Here the primary of that built-in transformer or coupled inductor is in parallel with this main switch, and the secondary is connected in series with the load. And here as the primary side voltage is less, here it is in parallel with the main switch, so that voltage stress across the switch is very less compared to the output voltage. The voltage stress across the switch is less. And also one issue in using the coupled inductor, although it can provide high boost up ratios, is the leakage inductance will cause sudden spikes in the voltage, which will affect the switches. So we are using one an active clamp circuit, that is active clamp capacitor, so that when the switch is off, this switch will be on, that is auxiliary switch will be on. When auxiliary switch is on, the sudden increase in voltage will be absorbed or absorbed by this clamping capacitors. This capacitor will be charged using those sudden spikes in the voltage or sudden increase in the voltage. So thereby we can reduce the effects of the leakage inductance here. And we have achieved ZVS here for the main switch and auxiliary switch. By achieving this, we can reduce the turn-on loss. In switching losses, there are 3 losses, that is turn-on loss, turn-off loss, and conduction losses. Here, if you see these waveforms, first waveform is pulse, second one is MOSFET voltage, third one is MOSFET current. Here the pulse will be on and off continuously according to the the switch will be turned on and off continuously according to these pulses. When the switch is off, that is when the pulse is 0, at the time the voltage will appear across the MOSFET. And when the switch is on, the MOSFET starts to conduct, so the current will be increased. But here in this, the voltage is going to 0 before the switch is turned on. Okay, when the switch is turned on, the voltage will reach 0 and current will increase. But here, before the switch is turned on, the voltage is reaching 0. So while we turn on the switches, the current is also 0, the voltage is also 0. So the turn on loss will be very, very less. It will be minimized here. By doing this, we can reduce the losses. And by reducing the losses, we can increase the efficiency. Here for auxiliary switch also same. We have to zoom it and check. Here also same thing only. Before the switch is turned on, the voltage is going to 0. and here the current is going below 0. That means the body diode of the MOSFET is conducting. So the switch current will be 0 only. That is, the MOSFET is not conducting here. Only the body diode is conducting. Here it is going above the 0 means the MOSFET starts to conduct. And this is the output voltage and current. Here the voltage is around 400 volt, current is around 0.63 amps. This converter is designed for the power of 250 watts. Here we can check that efficiency, input power, output power, we can check it here. Okay, first waveform is the efficiency curve. Here we are getting almost 94%, and load power is around 255 watts, and input power is around 275 watts or 270 watts. So here the efficiency is 94% for 250 watts power. Okay, the main thing of this simulation is we are using one coupled inductor or built-in transformer to increase the voltage step-up ratio, and also we are using one active clamp circuit, and that is active clamp capacitor, in order to reduce the voltage spikes appear due to the leakage inductance when we use coupled inductor. And also, as the coupled inductor is connected in parallel to the main switch, that is the primary of the coupled inductor is connected in parallel with the main switch, the voltage stress across the switch is very less.